Hello, Philip Newell.
Hello.
We are just excited to interview a person like you. This is not the first English interview we do. So I will try to speak the English as well as I can. And then I will subtitle our conversation for all Spanish people. Yeah, okay, so I think
if you can't say something in English, say it in Spanish, and I can.
We can mix.
Yes.
Okay. Maybe I would like to do an interview to you about your history and about the acoustics. There are two matters I really want to know about you. So, when you want to start?
Well, I became interested in music when I was at school, and I learned the piano for 5 years, formally being taught the piano. And when it was time to start considering going to university, I felt that I want to do something more connected with music and recording. And I looked at courses at 3 of the universities in England, which were Southampton and Surrey and Salford. But there was nothing really. It was mainly about broadcast and things connected with radio and television. There was nothing really connected with music recording. So before beginning the last year at the grammar school to take the final examinations before going to university, I found that there was a job available in a shop that was repairing hi-fi equipment, but it was connected. And so I told my parents that I'd prefer to work and not go to university, because this was the path that I wanted.
Mm-hmm.
And luckily they understood. And so I was going to the public library, looking for books, desperately trying to find more information about the things that I liked. And I got a job. I was offered a job in a ballroom, in a dance hall, where 3 nights a week, 5 nights a week in effect, they had live music. And so I took the job in the ballroom and got offered more work there, left the job that I was doing during the day, began to get moved to bigger ballrooms owned by the same company, until I eventually arrived at the Orchid Ballroom, which was a very big one in just south of London. And I was still trying to learn about recording studios. And one of the band leaders, who was the resident at one of the ballrooms, asked me if I could build him a small recording studio for just doing his own recordings. And I had friends by then that worked in the big recording studios in London, so they would help me and offer me advice. And this studio became much bigger than just a demo studio. And eventually I moved from there to one of the biggest studios in London, which was Pi Records. And Pi was one of the big 3, which was there was the EMI studios at Abbey Road, there were the Decca studios, and there were Pi studios, all in North London effectively. And these are the biggest 3 studios in the country. And so that became a sort of university for me, because it was it was a studio with 2 big studios, 2 copying rooms, 3 disc cutting rooms, 2 mixing rooms, editing rooms, and a staff of about 32 people, some of which were the most experienced people in the country. So I was learning in one of the top studios, and this was priceless information.
It is better than university.
It's better than any university, because working there with the real real big stars,
yes.
Having to work with all the pressure of the recording sessions, and things could not go wrong, and it was learning under pressure, learning how to deal with the situations as well as how to deal with the equipment and the musicians. So I enjoyed that. I enjoyed it a lot, and spent a lot of time with Pi's mobile recording studio also. And then I met a man called Tom Newman, who was also building a studio at the time, trying to build one for Richard Branson and the Virgin Records organisation. I think at that time Richard was only about 20 years old. Tom was about 28, which seemed really old at the time. And he was going through the same process that I'd gone through, that he couldn't find the necessary information that he needed, so he was relying on me to go out to Oxford at weekends and try to give more guidance. And then I was offered the job of the chief engineer at the Manor Studios when it first opened. I went there about 3 weeks before it opened in 1971. And that's how I became involved in Virgin Records. But still, the thing that was the big mystery to me was the acoustics. I could pull a tape recorder to pieces, I could pull a mixing desk to pieces, I was repairing the Neve mixing consoles and the Ampex tape recorders. I did some recording there, especially at nights, because I had experience as a live recording engineer as well as for live sound. So sometimes I got asked to do late sessions in the studio if an engineer was ill or something like that. But the thing that was still mysterious was acoustics, and nobody could really explain things in a way that I had 100% confidence in what they were saying. So when we built the Manor, it operated for about 4 years in its original state. But during that time, we'd recorded Tubular Bells, which went on to sell 15 or 20 million copies. And that provided a lot of money to rebuild the studios, to improve them. Excuse me. So I went to see Tom Hidley in California at the end of 1974, and he seemed to have answers to a lot of these acoustic questions. I went over to see some of the rooms that he built in the United States and in Canada. I went back to the UK and convinced Richard that we ought to ask Tom Hidley to do some of the work and rebuild the Manor. So in the end, what Tom wanted to do was very Californian, and we all wanted to keep some of the English countryside in the... So Tom effectively designed and built the control room, and we left him to that. And it was a combination of several of us who built the recording studio. Some of it was Tom Hidley, and there was also Mick Glossop and Alan Perkins, the chief engineers of the Manor and the Mobile, who put a lot of input into it. And that was an enormous success. The Manor became a legendary studio, and people there like Queen and Elton John and Gene Simmons from Kiss, and just so many people, so many big recordings were done there. But still, there was a mystery about acoustics. And in 1982, I eventually left Virgin. I'd been the technical director of the recording studio since about 1974, it was 1974, I think. Also being responsible for building the townhouse and the Manor Mobiles and several other Virgin related facilities. And I spent a year more or less concentrating on the flying, the seaplanes and things.
Yeah.
Because I got involved in that when Richard planned to build a recording studio in the British Virgin Islands. So that was also very interesting, but it never happened because the tax situation changed and Virgin were expanding into many other areas. And that was one of the problems, because I didn't like working in big business, and Virgin Records was becoming big business. And so I wanted to do something that was still more creative, and so in 1984 I was asked to build a studio for Jacobs in the south of England. And at the townhouse I'd used a lot of Tom's ideas, but added some of my own in the disc cutting room, the first disc cutting room at the townhouse. And I started thinking more about loudspeaker design and particularly control room design. And I still, even almost 20 years after I'd begun, I still didn't fully understand what about the acoustics. I could do things by experience and know that they would work, but I didn't really know how they worked, and not many other people did either. So in trying to design a new set of, I was designing a new set of monitoring systems for the original Reflection Arts, which was a company based in London. And I realised that even in the loudspeakers I needed to know more. It was no use continuously trying things and seeing if it worked, and then keeping the good things and then changing the not so good things, and then sometimes when you change the not so good things, the good things were not so good. It is difficult to continue like this. When I was renting a house at the time from a person who was an aerodynamicist, and I'd been flying in an air display on Southampton Water, and the organiser of the display was Stephen Wolfe, was a designer of transonic wind tunnels. And so I spoke to him about some of my questions about horn design, and thinking, well, I know there's no airflow, but sound comes down them at the speed of sound, and some things just don't seem to be right. And so Stephen he offered to rent me his house because he was going to work for NASA in the United States. And he offered to put me in touch with the people in the Department of Aeronautics and Aerodynamics at the University of Southampton. So I went to speak to the people there, Professor Bob White, and I didn't know at the time, but in the building where the Department of Aeronautics and Aerospace was sited, the rest of the building was occupied by the Institute of Sound and Vibration Research, which was probably the biggest acoustics research facility in the entire world. And so Bob White said he thought I ought to go and see the people at the ISVR, and he put me in touch with Frank Fachi. And so I spoke to Frank about how we could try to get the answers to some of these outstanding questions. And that was how I first got deeply involved in acoustics. because Frank decided that what were the questions that I was asking could really only be answered at a PhD level. It was not something that undergraduates could work on. And by coincidence, he'd just told a student about 3 weeks earlier to go and find himself a job, because after the student had graduated, he wanted to know if he could do further studies on horns.
Mm-hmm.
And Frank said, "Don't be ridiculous, nobody does research on horns anymore." But as I said, about 3 weeks after that, I arrived at the university wanting to do research in horns, or wanting to pay for it. So Frank called Keith Holland back to the university, and we had a meeting. And after several meetings, it was decided that Keith would... okay. So it was decided that Keith would then do a PhD. I would pay for Keith's PhD, which cost about the same as a house in those days. And he would study exactly what I needed to look at in trying to design horns to develop better monitor loudspeaker systems. So that was very, very interesting work, and in all that took about 5 years. But during that time, I spent a lot of time at the Institute of Sound and Vibration Research at Southampton University, and that was one of the most amazing experiences in terms of truly learning about acoustics, surrounded by some of the best people in the world.
Mm-hmm.
And then one day Frank came to me and said, "Philip, I know you're already paying a lot of money for Keith's PhD, but we have a student who is very good. He's Brazilian, and he's halfway through an MSc. But the Brazilian government have not paid his bills, and the Home Office of the British government say that unless they pay his bills, they're going to expel him from the United Kingdom." And he said, "This is sad because he's a very clever student," and he was called Luis Suarez. And he said, "Is there anything useful that you think that Luis could do for you?" So, as Keith and I were working on the monitor loudspeaker problem, I contacted Tom Hidley, who was working on his infrasonic rooms at the time, when he wanted the rooms to be flattish down to about 10 hertz.
Yes.
I said, "Tom, do you fancy co-sponsoring a student to look into the whole concept of how the traps work with all the panels?" So Tom came over and we had a meeting, and he said, "Okay, well, let's do this." And so I went back to the university and I said, "Yeah, okay, we'll pay between us. We'll pay 50-50 we'll pay Lewis's course, so that he can stay in the United Kingdom and complete his masters." So that was the first serious investigation into the acoustics of the control rooms.
Mm-hmm. In the non-environment.
Yes, exactly. And so Frank Fahey decided that we cannot possibly do computer modelling because we don't have the input data, we don't have the information. We'll have to build a model. So we'll build a model at 1/10 scale, and we'll start investigating the elements one by one. But the problem is that the acoustic properties of a lot of materials will not scale.
Yes, by the wavelengths.
By not only that, it's because if for example you normally use 5 centimeters of glass fiber or rock wool, well, at 1/10 scale that will be 5 millimeters, not 5 centimeters. The problem is though, the fibers are still the same size.
Yes.
So you haven't scaled it down. the flexibility of the fibres you haven't scaled down.
The parameters.
The parameters do
It's
not
a
scale.
down. Yes.
They won't scale. So Luis completed his work, but he found that these panels don't work. And so there were only two possibilities. Frank had changed instead of using chipboard for the wood panels, he found that chipboard at 1/10th scale, the rigidity was not correct. Mm-hmm. The rigidity, it didn't, again, even the chipboard, even the wood did not scale. So we had to use a different thickness of aluminium with a plastic film on it to try to scale down the 1/10th properties of the chipboard. But even then it did not work. And Frank had said, well, we cannot put the fibrous materials on because the fibrous materials will not scale. So either Luis's model was wrong, or all the concepts that we had about how these bass trucks worked, or wide range trucks were wrong. And they checked Luis's model, seemed to be okay. So it was decided that the only way that we could possibly verify whether the model was correct or the concept was correct was to build a full-scale model. Now, of course, there's nowhere in the university to build a full-scale model. So in 1990 there was a company from Liverpool that approached me. They wanted a studio, but the money that they were getting, there was some grant from Liverpool City Council, and there was some charity money, and there was some money from the European Union, and it was supposed to be a public, a sort of public service, like an arts thing that was to help also unemployed people and musicians in Liverpool. And it was a project called the Liverpool Music House. And they had very little money, and they asked me if I could help to design it. So I came to an arrangement with them whereby I would try to do it for the money that they had if they would let me build the control room that I wanted to build. And in fact this wasn't very different from what Tom Hidley had done in 1982 in Japan, where he agreed to build 2 studios on the understanding that one of the studios he could build the way that he wanted it. But the client said, yeah, this is okay, but if it doesn't work out, if people don't like it, then you have to build it like the other one. And that's at your expense. So anyhow, I agreed with the Liverpool Music House that we would build this studio, and we used a lot of second-hand materials and all sorts of things. It was quite a big room. And coincidentally it was called the Lab. Not because it was our acoustics laboratory, because it was in a building that used to be a chemical laboratory for testing the mineral content in the ores that were coming on the ships into Liverpool docks. And when we built the full-scale model, it worked. Everything worked.
And what year was?
This was 1991. And at the same time, Keith Holland was finishing his work on the horn and finishing his PhD thesis. So, as he was finishing the work on the horn, we decided we'd put a monitoring system together using the horn into a room that Luis Suarez could model, could measure so that he could make models from the measurements. And we found that although his 1/10th scale model in the laboratories, the 1/10th scale physical model did not work, the full scale model did work. So that gave a lot more insight into what was happening, and we all went back to think about things. And then later another student, Stuart Coleham, he started looking at the findings of Luis, and he did a master's and then after he got the masters he went on to do a PhD, 3 more years on the same subject. So that was when Frank Fahey started thinking about things like the horn effect, and it was clear that there was not one single mechanism that was working. There were multiple mechanisms.
Yeah, complex.
Very complex. And it was Stuart that was the one that put the accelerometers all over the panels, and he found that, and Alistair Walter had done work on this as well in between. So Alistair Walter's undergraduate work was what led on to, he based that on Luis Suarez's master's work when it was Keith Holland was then a supervisor for Stuart Cole, and Stuart did his master's and then his PhD. So there's a whole chain of research, and they put accelerometers on the panels and found that at least 99% of the energy that was absorbed in the panels was re-radiated. So it was reactive, it wasn't resistive, there wasn't actually acoustic loss, the energy was re-radiated again. Perhaps in a more random way, or a more disorganised way, but it was still, it wasn't absorption. And so it started to look like the absorption actually took place inside the fibrous materials, but then all of the standard thinking up until then was that except in extremely large thicknesses you cannot absorb low frequencies in fibrous materials. But in the complex arrangement inside these trap systems, it was in fact doing that. And Tom Hidley had told me that the origin of the word trap was that he was working at JBL with Bart LeCanty. And Bart LeCanty later designed the high frequency drivers for TAD. And that they were giving a lecture in a room one day, and a whole load of blackboards and desks hadn't been cleared out. And so they piled them all at the back of the room, waiting for people to come and move them because the talk was on a holiday. And that they suddenly found that this room, which was very, very bad for speaking in, suddenly was not too bad, and they were trying to think what was happening.
So he discovers accidentally.
Yeah, and Tom was talking to Bart LeCanty, and Bart said, well, with the way that we've got all these panels arranged at the back, when we put all these drawing boards in it's like the sound gets trapped in there somehow. And they put some loudspeakers in there, and somebody had made some modifications to some loudspeakers, and decided that these loudspeakers were really, this modification was great. And then people came in, because it was a holiday. They came in after the holiday to move out all the things that had been put at the back of the room. And so the people that had modified the loudspeakers brought in their bosses to come and hear what had happened and how much better the loudspeakers were, and suddenly they sounded bad again. So they called the people back to put all the equipment back in, all these desks and drawing boards and things, and suddenly the loudspeakers sounded much better again. And so that's when Tom Hidley and Bart LeCanty came up with this idea of the bass trap, because it was seemingly trapping the bass. It wasn't doing anything at mid and high frequencies much at that time, because it was all hard materials. But it was getting lost in there to some degree. Although later what we found with Stuart was when you had just panels, and we found this with Luis, and there was no other things behind the panels, then the panels themselves did not absorb the low frequencies. So there were all these different questions that needed to be answered. And by about 2002, when Stuart had finished his work, we knew a lot more about it. But then in 2004, I was asked to build one of the rooms at in the acoustic laboratories of the University of Vigo. and we applied a lot of the techniques that we'd learned. And then the people in Vigo, once they had a room of their own, built with everything. We incorporated, it was a big room, so we incorporated everything we knew, and the room worked very, very well. But then what they had the luxury of was a full-scale model, all the measuring equipment, and a lot of students that were keen to do measurements. So it would have been about 2009, I think, where a paper was written for Acta Acustica, and that had a lot of new information that we derived from the tests in Vigo, because we had sound intensity probes and all sorts of things that we'd not been able to apply in the past, and we started to learn much more about the rooms, and started to learn how much reflections were actually the low frequency reflections in many ways were some of the worst culprits than the resonances. So not only did you have to get rid of the resonances, you had to really make sure that the reflections were. Some of them were not perceptible. It was quite strange, because some of them were perceptible and some were not perceptible, and depending on the direction they were coming from. And things like floor reflections became very obvious. But then a floor reflection comes back to you from the same direction as the source, so it doesn't affect the stereo imaging. And it turned out, after a lot of experiments, that the ear actually doesn't hear much of them either. So this we got a lot of very definite evidence of from Vigo, and it's a shame in some ways, because you see so many things on the internet now where people have got plots of their rooms and they have this dip and they're trying to correct it, and they don't realise it's a reflection off the floor, and it just doesn't matter. And you can't correct it with equalisation, because it's coming back with a delay. It's not like a resonance where where there are peaks and dips. The dips in a reflection are not able to be equalised.
With graphic equalisers?
No, you can't use them on any sort of equalisation, except perhaps some sort of digitally adaptive process. But then the problem, if you're trying to put that type of equalisation on, is the amount of boost that you need. And so you end up overloading the loudspeaker systems and making things worse. And there are some things which people are trying to control in the rooms, which not only you cannot control, but also you just do not need to control, because the ear doesn't hear them. You see them on the analyzer, but you don't hear them, because the first pass is still coming past your ear before the cancellation. Mm-hmm. And the brain locks onto this, and then it hears the reflection of a reflection. But you cannot measure this easily, because at the lower frequencies the gates would be open for too long, you'd pick up too much. They look bad on spectrum analyzers, but we don't hear like a spectrum analyzer. And we got a lot of this from the work at Vigo University, in terms of what things to concentrate on controlling and what things to completely ignore. So it was a total of about 20 years between Luis doing the first tests on these systems in Southampton and doing some measurements on the full-size permanent installation in Vigo.
20 years.
20 years, from 1989 to 2009. And it's really not surprising that there's not a lot of simple calculation can be done about these, because they work very effectively, but they work in complex and overlapping ways. And in many of the ways, if you change the characteristics so that something is not happening, so you can measure the other thing in isolation. You actually change the other thing that you're measuring anyway. So yes, several papers have been published on how these things function, and they certainly do function. But it was about 1959 when Bart LeCanfey and Tom Hidley stumbled into the possibility. And it was 20 years later before we had any real workable understanding of how they function.
But Tom Hidley never investigate about how it works.
Well, he did co-sponsor Luis Suarez with me,
okay.
so yeah, he did put the.
But not by himself.
But not by himself. He did, yes, because he had the people doing the constructions. He had them change things in rooms, and measure and listen and change things again. But it was all a process of trial and error. And this process is very valid. I mean, that's how people learn to build aeroplanes.
Yes, it's like aerodynamics.
Aerodynamics, it was impossible to calculate it at the start. They had to use trial and error. And only by finding things that worked could they then later start to work on the mathematics of it. And so if Tom Hidley had not put all this effort into trying to make systems that worked, then it would not have been possible to build the models later. Nobody would have thought of doing it. But when you get something as complicated as aerodynamics, you've got to build the working prototype first before you can calculate it.
And where did you learn about the panels? Did you see to Tom Hidley?
It was when we built the Manor Studios, yeah.
So you see when he was working.
Yeah, and then we built them into the townhouse in different ways. And then it was some years later that it was about 1982 in Japan when Tom first got the idea of putting the panels in at angles instead of straight, and he was getting better results. And a coincidence, around the same time that people like Shozo Kinoshita and Sam Toyoshima were building rooms in Tokyo also, and in these rooms they were all of low decay time, much lower decay time than had been traditionally the case. So Sam Toyoshima was starting to propose large control rooms with only 250 millisecond decay times. So a lot of things were happening in Japan all at the same time. So I think that was partly an inspiration for Tom Hidley to start lowering his decay times. And when he started lowering the decay times, he started finding that making the traps, putting all the panels at angles was more effective. And everything is...
Yes. Interrelated.
Everything is interrelated. There are a lot of people doing different things at the same time and sharing the information, or at least discovering the information of things that the other people were doing.
Why did you think that the angle of the panels is better? Because maybe major frictional zone, or maybe because it do a trap?
If you don't have the panels at an angle, you cannot get the horn effect.
Okay, so
because in both sides of the basically, if this is the wall and the panels are like this parallel, then when the sound enters, it hits the wall at the same time
and reflects.
But if the panels are like this, then the wave is bent, goes down the panel, and it hits this side before it hits that side. But on the other side of the panel, then the wave that's gone down the other side of the panel is then out of step. So then you get a phase difference on the two sides of the panels, and this is what causes the pressure difference that has to equalise through the fibrous materials at the back.
This is the horn effect.
This is effectively the supposed horn effect.
Okay, so the difference between the phase of the two
sides of the panel
of the chipboard.
Yes.
Okay.
It's the difference in the pressures causes an airflow through the fibrous material, and the fibrous material is acoustically resistive. It's resistive to the airflow, and this dissipates
the energy.
This dissipates the energy.
And the difference between the phases are due to the path or due to reflection?
It's due to the waveguide effect of the panel, because once the wave comes from the loudspeakers and hits the face of the trap, it then has to turn to go. Yes. It cannot pass directly through the panels.
They guide
the waves. And then when it arrives at the end of the ducts, it's at different phases, at different sides of the panel. The reason why this is more important on the rear wall is because if you have a low frequency sound, usually in the centre, in the stereo, then it's generated from 2 loudspeakers. And those 2 loudspeakers send the sound across the room, and it hits the rear wall. It's perpendicular to the rear wall. And also it's exactly in phase from the 2 loudspeakers. Yes. when it strikes.
The reflection.
Now on the sidewalls, well, the sidewall this sidewall, it'll receive the wave from this loudspeaker before it receives it from this loudspeaker, so there's not a simultaneous impact, and it will also receive it more at an angle. Mm-hmm. So the sidewalls do not receive a simultaneous impact. The ceiling does, but again, if you have the panels,
it's the same as the rear.
It can go. We don't angle. The tendency is to angle the panels pointing towards
the
loudspeakers, so that you look from the loudspeakers and all you can see is the thin line of the panels. You can see all the ceiling. But once the sound is in there, then it cannot reflect back down the same path, because there's no surface at 90 degrees to the expansion to reflect it back. It's lost into the system. So again, it's a form of trap. And at some frequencies, it seems like there is a surface impedance, whereby the whole entrance to the absorber, it doesn't see the things as being separate sections. There's a whole impedance, and this is another reason why for any change in impedance you'll get some sort of reflection back. This is why
the impedance in the enter of the waveguides is just on the rear.
It's different than the impedance travelling through the air, but there is a sudden change when you get to the front of it, and with the ceiling being angled, you cannot do this in the rear because you need it symmetrical. But the 2 speakers are at the same height, so they both arrive at the ceiling at the same time, but angled. It's not perpendicular. Yes. It's not 90 degrees to the ceiling. So that's why the systems are different on the sidewalls and the ceiling and the rear walls, because they receive the sound at different angles of incidence from the loudspeakers, and some of them receive them simultaneously from the 2 loudspeakers, and some of them receive them sequentially, with the closer one arriving first.
And the sidewalls are also angled?
Usually, but if you have, it's not often that you have a low frequency sound coming out of one loudspeaker in stereo. Usually it's coming out of the 2. So you're not driving the room from a single source. From the side to side modes, you're actually driving them from 2 separate sources. And in some of the modes, some of the frequencies actually cancel, because you're driving them from 2 points.
In the middle.
One might be driving on the downside and one on the upside of the pressure, and it cancels. And so there's not as much demand for high absorption on the sidewalls at low frequencies as there is on the ceiling and the back wall.
But there are some designs in studios like Peter Antonio Reflection Free Zone that use the geometrical theory to guide the waves out of the center.
At low frequencies it doesn't.
Yes, because the wavelengths seeing the sidewall like a plane.
Yeah.
But maybe the low mid frequencies.
And so with those designs, in order to operate over a reasonable frequency range, the rooms need to be quite large.
To angle the sidewalls.
To angle them and to get the, yeah. And Bob Walker at the BBC, he did the controlled reflection rooms, which were also quite complicated and angled to try to... But those were concepts still, in the early days, they were still trying to keep the control room with a decay time of 300 or 400 milliseconds, because traditionally it was thought that you needed that sort of natural sound in a room. And this was the reason for using diffusers, to try to keep up the decay time whilst avoiding the worst reflections.
And the concentrated energy zones.
There are concentrated energy zones. I mean, Jamie Angus showed in his work in the 1990s how in small rooms you have to be careful using the diffusers, because in some angles they actually concentrate energy more at some frequencies at some angles than a flat reflective surface. I don't like using diffusers in small rooms. I can hear them. It's a coloration. I don't want that energy coming back.
Mm-hmm.
I generally don't like the mathematically based diffusers. They don't sound the way that they measure. And that's what I was saying earlier about the floor reflections. They look horrible on a measurement, but they sound okay. And with some of the diffusers, they look okay on a measurement, and to me they don't sound right. And so I just do not like diffusers in small rooms.
In a small, but in large rooms?
In large rooms often you don't necessarily... It depends on the room. It depends on what you're going to use the room for. Yes, there's diffusion in concert halls if there's a lot of ornamentation in the room. But these days it's very expensive to get people to make nice looking pillars and statues, so it's easier to put up some diffusers.
Now it's totally without any ornament.
It's a difference. So yeah, they can be useful in situations like that. But diffusers I find better in large rooms, more practical in large rooms than in small rooms. They look technical and they look great. You can look at a measurement and it looks like they've improved the measurement, but then to me it doesn't sound right. You can hear them. Mm-hmm. But as I was saying, in about 1982 there was this big movement in Japan with people like Kinoshita and Toyoshima and Tom Hidley as well, suddenly making big control rooms, maybe 50, 60, 70 square meters control rooms with 200, 250 millisecond decay times. And they were not using diffusers either. It was all, they were using different systems of absorption. Some broken up reflections, but it was a case of getting the decay time down. And in the 1990s, when I was first asked to, early 1990s, when I was first asked to build dubbing theatres for mixing soundtracks, again we were experimenting with taking decay times down. And in the early 2000s I had to build some rooms in Barcelona. And they would have been outside of Dolby specifications with those low decay times. But I went over to Dolby with in the UK with Keith Holland and with my son Julius as well. And we spoke to Dolby and told them we wanted to take the decay times down, and it would have been out of specification, but would they still accept the rooms and certify them for Dolby Digital? And after a lot of explanation, they said that they would. But it was like this situation that Tom Hidley had in Japan, where the owner said, if the engineers don't like this room after 6 or 12 months, you've got to put it back like the other room that we're building. What happened in Japan was the owner liked this room so much, he himself paid for Tom Hidley to build the other room, the same as a non-environment. That was the first non-environment room. That was the first two. And in Barcelona, this low decay time room, which was based on the non-environment concept. Tom Hidley had done one with me in Barcelona in 2001 or 2000. But Tom had still tried to keep these 400 milliseconds or so in the room, 400 or 500 milliseconds. It was a big room.
But in which frequencies? Because the reverberation time?
In the mid frequencies.
In 500?
Yes, around 500. Yeah. They were still up there.
But 500 is not real the bad components of the reflections, under my point of view.
But in the film world, they were still believing that you had to have higher decay times to represent the cinemas, because they were thinking that you can't mix in a room that is a lot different acoustically from the cinemas in which people will listen. But we were starting to get the multiplexes of cinemas with lots of small rooms, and decay times in those rooms was quite low. And we started thinking that really we could get better mixes, quicker mixes, if the decay times in the dubbing theatres was low. And what happened in the case in Barcelona in Soundtrack was the low decay time room, which was really the B studio. With after about 6 months, people were asking for that room as their first choice. And so Dolby then. In the UK, they removed the requirement for the bottom limit on the decay time. So they took it out, and in fact they'd been building a room of their own, a test room, a test theatre, in their own laboratories in the UK with a low decay time. And I was one of the co-writers of a report from the SMPT in 2014. And one of the main rooms now at Skywalker Ranch in California, again, it's got a 250 millisecond decay time.
In 500?
Yes.
But it is not better to measure the reverberation time in very low frequencies near the modes?
It's quite low. It's only down about 500 milliseconds in the 63 hertz region. It's quite low. It's difficult measuring the decay time and the low decay time in these rooms, because if you start to do narrow band analysis on it, the decay time in the measurement filters can be greater than the decay time in the rooms. So it's not easy measuring the low decay times at low frequencies. But the sensation is of a much tighter low frequency sound. And the general trend with cinemas now is that people build cinemas with relatively low decay times, because when you get all the surround sound and even the immersive sound systems like Dolby Atmos and Auro 3D, if you have sounds coming from many different directions, if the decay time is higher, you start to lose the directionality.
Maybe the early reflections are involved?
Early reflections, late reflections, reverberation, because if you've got reverberation in the room, it affects the reverberation that you're hearing from the source, and so you lose the definition in the immersive rooms if you've got this thing about control rooms, even big ones, having needing to have decay times of 400 milliseconds. It's gone. It's still all over the internet, but it's gone. It's not the way that professional rooms work.
Mm-hmm.
And yet still you keep reading about... this is the other thing about universities and institutes, and they want everything formalised. And people start... Architects and their consultants start writing the requirements for the control rooms and in universities and institutes. And they're still saying, right, well, the control room has to have a reverberation time of 400 milliseconds at 500 hertz. Where did they get this from? The industry doesn't work like this anymore. But the problem is there are no written standards. And so when you're doing an architectural proposal from a university and everything, you have to say, well, this is a standard according to this document. But there are no documents to say how professional recording studios and professional dubbing theatres where they mix film soundtracks, there are no documents to say how they work. And the documents that do exist are antiquated. They're effectively out of date. And they're not enforced inside the industry. And yet the people building the rooms in the institutes are finding the closest document that they think might be relevant, because they have to justify it to the administration of the institute.
Yes.
And they're building nonsense.
With the normatives.
They're building nonsense. These things are gone. They're 40 years out of date. But nothing has officially replaced them. So it's really sad, because in a lot of places students are being taught in rooms that are not good. And they're not good because the administrators rely on the consultants to provide all the relevant background justification, and we're working in an industry that doesn't have a lot of that. When we built some of the best studios in the world, we didn't build them to a specification.
The less the reverb, the better.
That was the way that it slowly went. It slowly went down, 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 down. And when I built the first room, the first control room at Majestic in 1970, then I thought that the decay time should be low, and that's the way I built it, and it was a big room. And people came in and said, oh, this is very dead. We're not accustomed to working in a room like this. I said, no, but it's so easy to work in. And because it was a new studio, the owner started to panic a bit about it, because people were saying, oh, it's very dead, it's very dead. Well, it's no more dead than the rooms that we build now. But at that time, people were thinking always in, well, the BBC specification for a broadcast control. What's a broadcast control room got to do with it?
This is not a broadcast control.
And even then, you see, somebody who used to work for Neve sent me a photograph last year. I'll get you a copy of the photograph. And he sent me a photograph of the control room at Cine Telly Sound in London, which later became the company CTS that took over the music centre at Wembley. And they were very famous for recording music for film. And they did music for James Bond films in there, and Henry Mancini was in there, and Burt Bacharach and John Barry and all the best. And so this was the control room. And I mean, if you see the photograph, I mean, you'll fall about laughing, because there was a row of tannoy monitor loudspeakers fixed up in the corner of the front wall and the ceiling, which is like the worst possible place to put
The maximum pressure.
The low frequencies must have been all over the place.
Maximum
all the surfaces of the room were hard, except for some drilled chipboard panels, wood panels, which were partly absorbent at mid frequencies. All the equipment racks were in the room. A big solid Neve desk in the middle of it.
Huge furniture.
huge racks, steel racks and everything. Well, in those days, the only acoustic measurement you could make was reverberation time. There was no equipment to make any other measurement.
Electronic equipment.
Electronic, you could... There was no such thing as a real-time analyzer to look at the spectrum. You could do it, recording it band by band and then taking it away and measuring it in the laboratory later. And you could build rooms which all had the same decay time and all sounded completely different, with different resonances and different peaks and dips in the response and reflections coming from different directions, but it was all they had. And so when I built that room in 1970, all that they had was the reverberation time should be, and I built a great sounding control room that was really neutral, very, very clear. But it didn't have the standard and the reverberation time. And the amazing thing is that 45 years later, people are still saying that a control room needs 400 milliseconds decay time. It's absolute nonsense. It's complete nonsense. But it's like it's become a religion now. People believe it. It's like somebody came down from a mountain with a big piece of stone that said, "The control room shall have 400 milliseconds."
like Moises.
And that's and it just is not like that. We don't build control rooms like that, not even the biggest ones.
And you usually measure the reverberation time, or did you use also spectrograms, waterfalls?
No, because the point is that once you get the reverberation, the decay time, it is decay time because there is no reverberation. Because strictly speaking, reverberation has to be a diffuse field.
Yeah.
And with the decay times so low, some of these sounds never even have the time to bounce even once off every surface before they disappear, before they're absorbed. So it's a decay time. But yeah, we still use sometimes the term reverberation time. Once it gets down to a level of about 200 milliseconds, it doesn't matter if it's irregular a little bit, because you don't hear it. So if you've got a 400 millisecond reverberation time at 500 hertz, and then it goes up to 500 kilohertz, and then down to 302 kilohertz, and then up to 4 again, then yes, you can hear something's not right in this sound. But once you get down to 200, then if it happens to go up to 220 and down to 180, and the difference in real terms of 40 milliseconds is so small that you cannot hear it. So again, the old concepts about you have to scale make sure that it doesn't move more than 10% or whatever, it's nonsense, because even 20% of 200 milliseconds is only 40 milliseconds, and you can't hear a difference of 40 milliseconds between bands in a decay time. Mm-hmm. So once you can get things under control, there's not a lot of measurement that you need to do, because there's no activity there to disturb anything.
And you focus to control
the widest frequency band possible.
The widest?
Yes.
Okay, so not only on the low frequencies?
No, because the idea with the non-environment rooms is that if the main reflective surface is the front wall, And if the loudspeakers are built into the front wall, then they cannot reflect off the front wall because they're built into it. It's instantaneous, all the sound goes away from it. But when you're inside the room and you're moving something or speaking, then you get a reflection off the front wall. It feels like you're in a nice, pleasant environment. And usually we use a hard floor, so you get reflections coming up off the floor. So you get reflections coming off the equipment, you get reflections coming off the front wall, you get reflections coming off the floor. And when you're speaking, your voice sounds, it doesn't sound like you're in an anechoic chamber. It sounds quite natural. But when the loudspeakers are set into the front wall, then there's very little reflection off the equipment. Certainly nothing's coming back from equipment at the sides. There's no reflection off the front wall because it's all going forwards, it's all pushing away from it. And the reflection off the floor is largely inconsequential because any higher frequencies come back up from exactly the same direction as the loudspeaker, so they do not disturb the stereo image. It doesn't smear the horizontal position. And because the low frequency dips are something that the ear counts as natural, because we spend all day on a floor, most of us. Very few people are awake during a time when they're not on a floor. And so floor reflections, we've evolved over the years to ignore the floor reflections.
Yes, because the ears are not so sensitive to the vertical plane.
And also, if we have some predator coming after us, if there's a tiger after us or something, then we need to know instantaneously, is a tiger over there or where. But what we do know is the tiger is not going to jump out of the floor. So there's no need for human beings to be conscious immediately of something coming up the floor. Things don't come out of the floor at us. A snake occasionally perhaps, but if a snake were on grass or something, we cannot see the floor.
And why did you choose the non-environment for control rooms instead of any other design?
Luis Suarez was, as I was explaining, in 1989, he was doing this 1/10 scale modelling of the non-environment room. Tom Hidley was trying to build these rooms that were very low decay time, even at 10 Hertz. And he needed to get the systems more effective. But when we were first discussing what Luis might be able to do, I wanted to try to keep Luis at the university because he didn't want to be expelled from the UK, and he was a very nice person, really clever as well. And so we thought, well, he must be something he can do with the low frequencies of control rooms. So we arranged one weekend that Keith Holland and Luis and I will go to London, and we will go and visit 5 major studios in London, all with different designs, and we tried to do as many measurements as we could in these rooms, and then to see if we could find something that Luis could concentrate on, to try to study why these rooms sounded so different at low frequencies. And we went to Marcus Music, which was an Eastlake design, and we went to Olympic, which was the new Olympic studios after Virgin bought them, were designed by Sam Toyoshima from Japan. And we went to Britannia Row, which was the Pink Floyd studio. And that had Westlake monitors. Marcus had Eastlake monitors. Olympic had Westlake monitors. We went to a studio called Blackwing, where I'd modified the control rooms. and they had some reflection arts monitors, some of the big ones at the time, which I'd also designed. And we went to a studio called Nomis, which was Tom Hidley's first non-environment room in the UK.
Mm-hmm.
Or effectively it was. I think it was a mastering room before it was the first big one. And so we took some CDs with us so that we could also listen to these rooms, so we'd have measurements and we could also write things about what we were hearing. And when we got to Nomis, with the Kinoshita monitors and the non-environment control room, we just all looked at each other and thought, but what we're hearing on the music, it cannot be that this room is making the music sound good. What we're hearing, it can only be that this is the only room where we're actually hearing what is recorded on the CDs. And we heard so much definition in the sound, such a good stereo imaging, the bass was very tight, and we were noticing a big difference in every CD. And in some of the other control rooms, what we were hearing was, well, this control room, the bass tends to sound like this, and in that control room the bass again. And in the non-environment room at Nomis, every single CD had a different bass sound. It's not the room. This room's completely neutral at the low frequency. We're hearing actually what the bass is recorded. And
only the effect of the loudspeakers.
Yeah.
Not the room, only
not the room,
speakers.
just the loudspeakers. And it had a gigantic solid-state logic mixing console and studio tape recorders, and so we had a meeting the next week at the university, and we abandoned all this idea about Luis doing a study of why the bass sounded different in each room. And that's when I contacted Tom Hidley. I said, Tom, this room at Nomis, it's unbelievable. We've never heard this clarity before. And that's when I asked Tom if he would go halves with me, pay 50% each to sponsor Luis Suarez, to do a master's thesis just on the low frequency control of that non-environment room. So that was the first time that I'd heard it, and we just dropped all the plans for Luis to do the to try to decide why all the other rooms sound different, what it was in the characteristics that gave them the sound. Forget those other rooms. Let's concentrate on how does this room work, because Tom couldn't tell me. He said, well, I build these bass traps and then put these here and that there. Yeah, but how do they work, Tom? Well, I think they do this and that and that. But he couldn't tell me. So I said to Tom, well, look, if we can find out how they work, then you can apply this to your design of the infrasound rooms, and you can maybe use this knowledge to make the absorption more effective down to the lower frequencies. So understanding how they work, it'll be useful for me if I can incorporate them into smaller rooms, and it'll be useful for you if we can incorporate them into your lower frequency rooms. So from then on, I never built any other room except...
No.
Yeah.
Okay, it's real a bass trap, the hangers, they traps the waves, the acoustic waves?
It's wide band. It operates from the low free, even at 20 kilohertz it's still absorbing. It's a huge absorber, a wide band absorber. Okay,
but for example, if you leave the rear wall without the membrane?
No, it doesn't. Well, if you leave the wall without anything and it just goes into the outside air, then yes, it traps.
For example, with a plasterboard, the hangers work without the membrane? If only put a plasterboard?
the bottom frequency to which the hangers work, the panels, the hanging panels work, depends on the depth.
Yes.
Right. So, if we could make these panels 3 meters deep, then yes, they would work to lower frequencies. But this is not usually practical. So, the way that we build the walls behind the panels is that frequencies below about 50 Hertz begin to be absorbed by the walls. The whole wall, effectively, it's not just the materials on the panels.
It's a diaphragmatic.
The whole wall is diaphragmatic, and so you get the dead sheets which are absorbing some of the frequencies. The plasterboard which is absorbing other frequencies. The whole wall itself is absorbing even lower frequencies, and the idea is that the layers that are absorbing the mid frequencies but let the lower frequencies through, those are the first, and then whatever passes through then gets absorbed by another system, and whatever passes through that gets absorbed by another system. So the system of lowest frequency absorption has to be at the back. But again, if you're trying to calculate this, then I've said in one of my books, in fact it's in one of Frank Fachi's books up there, could be Engineering Acoustics or Foundations of Acoustics, in one of his books up there, he actually says that once you get beyond a single plasterboard on a frame, then mathematically it becomes very, very complicated to, even if you put a second plasterboard on or a dead sheet in between, because there's so much variety in the nature of the materials themselves. There's so much variety in the amount of contact between them, how far you put the screws apart, whether you use metal studs or whether you use wooden studs of the frame, and you can never get the information as to for how these things are put together. And it's no use saying, well, I measured 2 square meters of the plasterboard and it's got this characteristic. It doesn't have that characteristic when it's put on a frame. It doesn't have that characteristic when you've put a dead sheet on it. It doesn't have that characteristic when you've put another plasterboard and made a sandwich. So you cannot get the basic information to do a calculation.
Yes, but the system you are describing me, the membrane, the first wall as a diaphragmatic resonator is I think that it is maybe more an isolation system than a control room system.
It depends on the weight of the dead sheet. If you put a heavy dead sheet in between 2 heavy plasterboards, then it will reflect most of the sound back into the room. If you use a lighter weight dead sheet and thinner pieces of plasterboard, then you can allow these things to vibrate. They will not isolate as well, but they will absorb a significant amount of sound.
Okay.
So if somebody comes to me and they said, right, I need to absorb the low frequencies in this room. So I said, well, do you have any neighbours? And they say, no, there's a warehouse next door, but they don't mind about anything. So you can concentrate on using materials which will absorb, but by vibrating they will transmit some of the sound through, but that does not matter. But if someone has an identical building and they say, well, yeah, next door there's a company of lawyers and they have a lot of meetings and they like everything to be silent, then you have to put heavier materials in that may not absorb as well, but they will isolate more. So if there is not a lot of room if there's not a lot of space in the room to then put more absorption on the inside, then this room cannot be as good as the other room in terms of the internal acoustics. And that's why in the books I've written so many times, it's important to have sufficient space. If you need isolation and good acoustic control, you need to start with a big room. You cannot say, well, I've got a room of 20 square meters and I want the greatest possible isolation and the greatest possible control of low frequencies. You cannot do it.
You do not have the space to
You just have not got the space to do it. If you've got the space outside, even if the walls are quite resonant, then that can even let the sound go outside. And sometimes quite small rooms can be very controlled at low frequencies if you can let the sound go outside. If you've got a big garden or something and nobody else is going to complain in the house. But if you want a small room in a house and the owner's wife wants to sleep upstairs or something and doesn't want to hear the music, it's very, very difficult.
You need to isolate.
You need to isolate. And once you've isolated, maybe there's not space to really get the sound that you want. You can't do it. There is no magic. You cannot do it. Then we've built great small rooms with not very good isolation. But it's difficult. You can you can go a long way towards doing it, but it gets very, very expensive. And usually, the reason people are using a small room is they do not have the money for a bigger one.
And you use for isolate reflections or maybe absorbs?
No, you cannot really use absorption for isolation, because if you put 90% absorption, if you've got a wall and it's 0.9% absorption, and this wall is 0.9% absorption, then what comes off that wall will be only 10% of what you started with. And then when it's reflected back off that wall, it's only going to be 10% of 10%. It's 1%. So off the second bounce, it's 10 dBs down. It's 20 dBs down. So it's great control for the room. But 0.9 absorption is only 10 dBs of isolation. And 10 dBs of isolation is no good to the next room if you want to work here at 90 dBs.
Yes. But you usually...
So if you wanted 40 dBs of isolation using absorption, you'd need an absorption coefficient of 0.999, almost perfect absorption. You can't do it.
Yeah.
You need enormous space.
Huge.
Again, I've written in the books, if you wanted something like 60 dBs of isolation using rock wool, mineral wool, you'd need walls about 10 meters thick.
So you use reflection.
So you have to use reflection. It's the only
impedance change.
Yeah, the only way you can get isolation, practical isolation, is reflection. But as soon as you start to put in the isolation, the sound isolation, what you're doing is you're building yourself a reverberation chamber.
Yes.
All the time you increase the sound isolation, you're increasing the decay time, the reverberation time in the room. So you're making you're making the problem of controlling the sound inside the room much worse.
The perfect control room situation is an open room.
Yes, it's more or less a free field. Yes. But that would sound a bit unusual for people to work in. So again, as I say, if you've got a hard floor and a hard front wall and your equipment, it gives you the sensation of being in a room, being in a space. But these reflections do not affect the sound of the music coming out of the loudspeakers.
So
that's why it's non-environment. You've put the loudspeakers, in an environment that does not exist, or exists to only the minimum degree for the loudspeakers. But the people working in the room are in a pleasant enough environment. It's non-environment for the loudspeakers, but it's a pleasant sounding place to work in for the people who are spending 8 hours a day in there.
So, for example, the best isolation system is a totally rigid wall.
Yes.
Because it has an infinite impedance.
If it's totally rigid, then it cannot pass the sound through. It cannot vibrate. But there are no totally rigid materials. And in one way, the way that we get rigid materials, we do use rigidity, but they tend to be heavy. So again, if you want high isolation in a domestic room, sometimes the materials that you would need to use are so heavy they will go right through the floor. The domestic buildings are not designed to take the amount of isolation, the weight of the isolation that materials that you need. You'd have to probably start in a room like this by putting 10 centimetres of sponge on all the surfaces, and you end up using 1/4 of a ton of contact adhesive or something like that, and it gets very, very expensive. Then you have other layers of plasterboard and other materials, but then you've got a very, very reflective room. So then if you've got 3 layers of plasterboard, it's heavy, it takes a lot of work, time to do it, so the cost of labour is very high.
The classical system of mass and a spring and a mass that you use for isolate, it's also used for the control room to control the low frequency.
It's more something that we use in the floors, where to isolate a floated floor from a.
But you use that system to control the low frequencies.
No, because the mass spring mass, it throws the energy back. It's isolation. It's not absorption.
Okay, so the non.
So you see, when you press a spring down, when you let go, the spring returns the energy.
It reflects the energy.
So what it does is if the spring holds the energy and returns it, then the energy does not pass through. So it's an isolation thing. It's not an absorption.
Okay, so
this is what people don't understand, because what they say is, "Oh, but Philip, I saw that you did this in this room and you said that was good." Well, but if I have 3 identical rooms, and as I was saying, if one room requires a lot of isolation, another one does not require isolation, one requires low frequency control, another is used only for speech, then if these rooms start off identical, then I'll build 4 different rooms, because the requirements are different, and if it's not a very big room, you cannot do everything well. So you have to concentrate on the important things in each room. So yeah, we use mass spring mass, but it's isolation, it's not absorption. It throws it back into the room.
Okay, but for the non-environment control rooms, you use the panels plus the membrane absorber and
yes.
all the wall, or not all the wall?
Yes, basically all the walls, except for the front wall, which is rigid and hard. All the other walls and the ceiling, they're all diaphragmatic. They all act as part of a very low frequency absorption.
Yes, but this is a mass spring mass. This must be an isolating system.
When you put the dead sheets into the walls, the dead sheets are damping.
The first dead sheet, the first membrane, or
all the dead sheets
Between the plasterboard?
Plasterboard itself, there's a lot of friction between the particles.
And
that friction between is a resistive loss.
Yes.
So these systems that are resonant, all the materials, that's why I do not use typical panel absorbers where you get a piece of plywood which is resonant. Almost all of these rooms are built with materials, big areas of materials that have a lot of high acoustic damping, the high internal losses. The plasterboard, the dead sheet, this is one reason why we use wood for the structure and not metal, because there's more loss in the wood. It does not resonate like a metal.
So in the control rooms, the first wall is maybe for the non-environment system than for the isolation?
Yes.
Or it works together?
Well, if it's very, very rigid, it will also act for isolation, the hard wall, but it's there primarily to give some reflection back into the room from the people speaking.
It works the first wall in a spring mass in a control room. You use it to control the very low frequencies that are not.
It's basically just mass. It's a rigid mass is the front wall.
The front wall?
Yes.
But the rear wall and the side walls are used for isolation?
It's used for both.
It's
used for both, and that's what I'm saying. If we need a lot of isolation, I have to use heavier materials, and that will affect the amount of sound coming back into the room. If there is not a lot of isolation, I can use lighter materials. This gives better absorption. It's always like this between absorption and isolation. Okay. But if you have a big room, you can get the absorption, a lot of absorption. But in a small room, you haven't got the space to put as much. So you have to balance between absorption and isolation.
Yes.
And that's why people say, but you did this in that room. Yes, I know, but that was different conditions. You have to balance as best you can.
Okay, another question I have is about the dimensions of the panels, of the hangers. You say that you can control very low frequencies if you increase the
depth.
Yes, the depth. So I think that it is a quarter wavelength system.
Yes, that does work.
Because it depends of the length. So you are working with a quarter wavelength.
Yeah, that's one of the mechanisms. It's definitely the quarter wavelength of the.
And how many mechanisms did you find in that system, in that complex system? The horn effect,
which we believe to happen at the back. Yes, there's the actual duct itself. Remember also that if the duct is lined with fibrous materials on both sides, then the wave passing down, the edges of that wave, it's passing through this thickness of fibrous material. And so the wave front gets slowed down at the edges, so it starts like this and it gets more. So you're starting to get phase cancellations, things out of step in terms of their phase. The reflected path coming back out is not the same as a reflected path going back in because of the angles on everything.
Yes.
So there are all of these mechanisms. The sheer quantity of absorbent material as well, the surface area of absorbent material is another significant factor. So you can add all these things add together. They all overlap in different frequency ranges. Mm-hmm. So you can get a very wide band absorber.
And did you identify which system, which mechanism is which every band?
To some degree, but the problem is that if you eliminate one part of the system, it changes the whole system. So So it's difficult. It's difficult to measure the things in isolation, because in order to measure one thing, you need to remove some of the other effects, and by removing the other effects, you've changed the system. It's not behaving in the same way.
But did you have any idea, or maybe?
Well, we tend to mount these panels about 35 centimeters between the front edges, and we tend to try and make them about 45 degrees to the back wall, and that this way, by measuring them, we've found that we get quite a good balance of the different characteristics.
Mm-hmm. And the last question is that if any person wants to improve the acoustics of his home studio, and he doesn't have enough money, for example 10,000 euros, which systems can he put in his home studio for improve the acoustics?
That's an interesting question, because you really need to deal with. Look, I mean, if somebody said this, okay, I'm going to put a really big absorber here. Well, it doesn't matter how good the absorber is here, if I'm still getting reflections off that wall and the ceiling and people often try to calculate the absorption, and they think that if they put a certain absorption in a room, then they can recalculate the decay time and everything. But you can't, because the absorption figures that you get for a material are the absorption figures were measured under standard conditions with a completely diffuse field. For example, it may have a material and it says its absorption at this frequency is 0.7. Well, it's 0.7 when a certain quantity of it is distributed over a reverberation chamber, and this is a typical way of doing it. And this is to maintain a diffuse field. But if you've got 10 square meters of it in the reverberation chamber, and then you put all the 10 square meters on one wall, then you don't have a diffuse field anymore, because there's nothing coming off that wall at all. And if you measure the absorption with the sound source here pointing directly at it, then you'll have much less absorption than if the sound source is going at an angle, because it then goes through the greater thickness of material. And so the official figures of absorption for certain materials only apply when it's distributed
homogeneous.
Yes, more or less.
Yes.
So if you take all this absorption and you put it round the room, then if you calculate the total absorption of the material, it's still the same. But it's not the same in the way that it affects the room. And there's a book up there by Trevor Cox and Peter D'Antonio about absorbers and diffusers.
Yes, I read it.
Right. And they sent something like 12 samples of material to 24 different laboratories. And there's an enormous difference in the absorption figures that they received back, because these things are measured under standard circumstances, but the circumstances they differ even in the rooms that you measure them in. It's not easy, and if you put all the absorption on one wall, it's even like when you put these corner traps. Well, frankly, how much of the room is it going to change if you put traps in the corners and you leave all these other plaster surfaces all over?
Not much.
So it's really, what I try to do is control as many surfaces as possible, and controlling the low frequencies, it needs a big area of low frequency absorbing devices. And really, until you've started to put significant absorption on 20% of the area of the room, you're not going to start to control the low frequencies. But probably the most important wall to treat is the wall opposite the loudspeakers. Because, as I was saying, the sound comes from both loudspeakers, it goes to that back wall, it strikes it at 90 degrees, which is the most difficult one to absorb. It strikes it simultaneously from both loudspeakers, and it comes right back up, and you're listening between that wall and there. You're absolutely between. And so if there's one wall that you must control, it's the wall that the loudspeakers are facing, the wall behind you. Mm-hmm. So if you haven't got money for anything else, put as much absorption as you can on the back wall. Mm-hmm. But it needs to be deep, because the other thing is that, I know this is inconvenient, but the depth of absorption depends on the frequency. It does not depend on the size of the room.
Yes.
So if I want to control 40 hertz and I need this, then even if it's a very tiny room, I need this.
Because the wavelength
does not change.
Yes.
I was explaining in an article last year that sometimes in very tiny rooms you can start to get things reasonably good again, because when you do not have a half wavelength, you cannot support a resonance. So if you have a room that is only 2 meters between the front wall and the back wall, there cannot be a resonance below a wavelength of 4 meters, because you can't get a half wavelength in the room. So in very tiny rooms, you do not need very low frequency absorption, because you cannot generate a standing wave at those frequencies. Mm-hmm. And the reflection that does come back will be so close in phase to the one that went past at very low frequencies that it won't cancel. So when you get a room that's 2 meters by 3 meters, you can in fact begin to get a good bass response again. But then there's not much room for people to work in there.
Okay, so after this interview, that I even want to make a lot of questions. We have our time expired.
Okay.
So I think that we have a lot of information. I recommend to buy your book, that there is a lot of information, and there are so many other topics that you have written about.
And that's why the book is written in plain language.
Yes.
Because it's impossible to just say, use this formula for this and that formula for that, because you cannot use these formulae because you do not have the information to put into them. And even the things that you have specifications for, they're only specifications under standard conditions. If you put them into different rooms, they'll behave differently. And one last thing.
Yes.
That the book is now also available
in Chinese.
In Chinese.
Yes.
So
I have this book.
In Chinese?
No,
right.
In English.
Yeah, and some of the others are available in Russian as well.
So anyway, thank you very much, Philip.
Okay.
I have learned a lot with you, and I expect that everybody, when see the video and read the subtitles, learn a lot as I do. Okay.
Okay.
Thank you very much.
Okay.